have Michael Hennecke from HPE present, and we'll see then if we can get Alex back online. Otherwise, we'll do some more scheduling, shuffling around. Yeah, we'll make it work. So let's go ahead, Michael.
All right, good afternoon, everybody. I'm Michael Hennecke. I am a solution architect in the DAOS engineering team, which a few months ago has transitioned from Intel to HPE. So I'm now in the HPE Cray Supercomputing Storage Systems division, which is the same place that also develops cluster store that is used at CSCS and many other sites. So the DAOS project actually started more than 10 years ago. I think 2012, Intel acquired VMcloud. And it was originally meant as a project to fix up performance deficiencies within Lustre. But looking at the problems and the possible solutions, the team pretty quickly decided that that is not going to happen by just incrementally changing Lustre. And DAOS became a project to develop a complete standalone storage system independent of Lustre. So there's some namespace integration. You can use it together with Lustre, some ease of use features, but it is not just a caching layer. It's actually a complete self-contained storage system. And I'll go a little bit through the architecture and the new innovative things that are in DAOS in the next couple of minutes here. I will not talk about HPE product plans. Those haven't been announced yet, but obviously we transitioned to HPE for a reason. There is work in the background to build like HPE branded and supported products around this. In 2023, Intel actually started broadening the governance for DAOS, which before that time really was pretty much an Intel-only thing. Most of the developers were in Intel. Argonne, as a big customer with the Aurora system, was engaged, of course, also from the very beginning. But other companies, including HPE, including Google Cloud, were picking up, doing co-development, investing themselves. So it was a reasonable move to change the governing structure and make this a DAOS Foundation project. The DAOS Foundation is hosted by the Linux Foundation. Every contributor is welcome. If you want to become part of the foundation formally, you first have to join the Linux Foundation, and then you can join the DAOS Foundation as well. And actually this year will be the first DAOS release where the scope is completely determined, and RPMs are signed by the Linux Foundation rather than Intel. So let's look at what DAOS is. First of all, the acronym stands for Distributed Asynchronous Object Store, and the object store in that term is a bit confusing because it is not an S3 type object store that pretty much everybody understands when they hear the word object store. So we tend to emphasize that this libDAOS API that's in blue in the middle here is actually a key value interface, right? And that is a low-level C language programming model API, and all the other data models are sitting on top of this key value, key array interface. So the object store terminology has given us a little, has increased community confusion because people typically tend to associate object with like S3 get put type objects. We do support files. Of course, everybody comes from POSIX, right? And that has to be part of the solution. But there's also block and object in the S3 term layered on top of the DAOS file system. To get traction, you have to do integration with middleware. So I'll highlight a few of those in the next few minutes here. It's, of course, a client-server architecture. We do network erasure coding or replication for availability. And we do support pretty much every network, whether that's an RDMA network or just plain TCP networks, of course, with different performance characteristics, but it's running pretty much everywhere. The focus was to cut out as much as possible of the traditional Linux block I/O stack. We are getting to a very efficient single server where in current generation hardware you get around 100 gigabit per second bandwidth and of the order of 1 million IOPS, maybe 500,000 IOPS, maybe a bit more. You may actually reach 1 million IOPS. And the design principles have always focused on scale out, right? If you want to support a system like Aurora at that scale, you have to make sure that everything scales, and I'll highlight a few of the design decisions. So in order to get there, probably the most important thing in DAOS is that we have no read, modify, write in the I/O paths, and we don't use locks. When you modify an object on a byte granular basis, we're actually writing the modified contents of that section of an object in a different place, and we store those modifications in what we call a versioning object store. So every write immediately goes into persistence, right? It's aggregated in the back. You don't have to wait for like read, modify, writes that very often happen in other storage systems, or have to lock regions of a file. Even if there's no actual conflict, you could create a lot of lock or token traffic. That doesn't exist in DAOS. We also don't track any clients. There's no dedicated metadata versus data services. Every storage engine has both functions, and you can scale as you scale the hardware. No global object tables, nothing that would be in the way of scalability. The I/O processing is pretty much non-blocking, and this is also exposed in some of the APIs on the higher levels. We do support distributed transactions in the native API. There is what we believe pretty much built-in multi-tenancy in the way that we are provisioning storage. We continue to add to that in terms of like more security features, but in itself, the way DAOS provisions, it's very amenable to multi-tenancy environments. And snapshots exist, and they can be triggered by the user. Like half of the administrative piece of DAOS actually lies in the hand of the user. They have a lot of control about replication, data protection, and also when they create snapshots or use snapshots. So one big change that happened was that originally DAOS was depending on the Intel Optane persistent memory technology exactly to store that versioning object store that was logging all the modifications to the objects. Intel has discontinued that, and that has taken us roughly half a year to come up with an alternate back-end software path that does not depend on Intel Optane persistent memory anymore. So what we're doing right now is we're just holding those data structures in DRAM memory on the servers, and then there's a write-ahead log to SSDs. So we have transitioned away from PMEM. Argon, of course, still uses that at a very large scale, but all the solutions going forward will just be DRAM and SSD, which also means there's no vendor lock-in anymore. In the early days, through Optane, there was essentially a vendor lock to Intel CPUs. So if we look at the way DAOS is provisioning storage, it's really a two-step process. The storage administrator creates a storage pool, which is just like a capacity that is provisioned across one or many or all of the storage engines in the system. And that is the first step where you can decide if you want to like physically partition your system so different groups get to run on different storage engines with SSDs behind them, or if you want to co-locate things. Within those allocated capacity regions, the user can then create what we call containers, storage containers, that bring with them a type. And the most prominent type would be a POSIX container, where you have files and directories. But there are many other types that can be imprinted into a container, which is essentially like a data set concept with the structures behind them. And all the containers in a pool share the capacity. There's no quotas on the container level. If one of them fills up all the pool capacity, then all the others also will get space events, essentially. So this gives us a lot of flexibility to have like all of the heavyweight allocation and controlling on which piece of my storage hardware does a pool actually live, to the traditional storage administrator or like a provisioning portal or wherever you want to do that, or a Slurm script if it's meant to be an FRML pool for just a job, or and then how that is used and how many data sets of which type the user wants to have in that pool, that's completely up to the user. And in case of HDF5, there's like many data sets that can live in different HDF5 containers, for example, in the same pool. What the middleware then does, and this is shown here with an example of POSIX containers, is directories and files eventually are just DAOS objects, and every object has an object ID, which is part user identifier and part is encoding the object type. Like is it a key value, is it a key array, and also the object class. Object classes control both placement and data protection. And again, this is user selectable. If you have you can do that on every object when you create the object. In a POSIX environment, of course, you can set defaults on a directory level, and then everything that lives within the directory gets a default type. This gives the user a lot of flexibility in fine-tuning. On Lustre, you probably know the striping commands to control stripe, right? This is way more powerful, but it's also something that we have learned is sometimes too much for a user, so it's really important that a site that runs this sets reasonable defaults, right? So not everybody has to go into all the details on how to fine-tune this. So looking again at the software layer, like above the server level, on the client, you just have a user space library, which is called libDAOS, which implements this key value interface. There is a system agent process that essentially discovers the server and does user authentication, but there's nothing in the data path. You just link with the libDAOS library, and you can then get access to your pools and containers. The libDFS library implements essentially a POSIX namespace. And a lot of the tools, including the S3 gateways, are living on that libDFS parallel file system implementation, so a POSIX container. But on the right-hand side, you see a few examples which are non-POSIX. One of them is Python. We have a Python container type, where you can essentially persist a Python dictionary from a language perspective to persistent DAOS storage. And you will never have to serialize, deserialize that. It will always be directly linked to persistent storage that can be like terabytes in size. There's an HDF5. I'll go into that in a bit more detail. And the yellow stuff, those are data models that have actually been created by different science communities. SecY is from oil and gas. FTB is the ECMWF field database. And Root is from CERN, I believe. So we are essentially just a registrar for a type in our software, and then they do all the data type mapping. So it's really powerful to specialize. When you have a community data model, you can just create a DAOS backend with that and then use the native APIs, and the end users just use the data model that they have always used. When we look at POSIX, this libDFS library creates something POSIX-like, but the calls are actually not POSIX calls. So to use DFS natively, you have to replace your read and write by DFS read, DFS write, essentially, right? So it requires code changes, but it gives you complete operating system bypass, asynchronous I/O, maximum performance, minimum latency, but it requires a code change. And the other thing that sometimes gets into the way is that the DFS layer doesn't provide any caching. By design, we designed this interface under the assumption that the data is so large that you have to go to the server anyway, but that's not always true. The pass number 2 is actually just using vfuse to mount a POSIX container in Linux. This will give you caching by the Linux kernel, which is sometimes beneficial. But Fuse itself is pretty slow because you have to switch to the kernel, right? You go through the virtual file system layer. So single thread performance with Fuse is definitely not good. It's more like a convenience mechanism, but in some cases, especially when you can benefit from caching, it's a good way to go. We implemented a middle ground with this, the pass number 3 here, where through LD preload, we can actually intercept all of the POSIX calls, both the data calls and the metadata calls, and transparently rewrite them to DAOS calls, the equivalent DAOS DFS calls, which means you still have a Fuse mount, but everything else goes to the native API. And that's what we typically recommend for people who start with DAOS. They have POSIX applications, so they do a Fuse mount and then set LD preload, and all the actual I/O traffic will use the fast pass going through the libDFS library directly. So that's the way how you use DAOS with a POSIX container. And then there's a lot of middleware sitting on top of that, including like data loaders in the AI space. The MPIO, ROM.io layer has a DFS backend and some other middleware as well. One thing I'd like to highlight here is that there's also a lot of community interaction, right? All of this is open source. Our code is BSD plus patent licensed. And there is, for example, a collaboration of the Hennecke labs from the UK and Google Cloud. And they have developed a PyTorch data loader that is interfacing with the native DFS environment. And they got some pretty impressive speeds ups on that. So this is a community contribution. It's not something that our team has done. what I wanted to focus a little bit on is the HDF5 Vol plugin. We had a chat in one of the coffee breaks here. The traditional way to do like parallel applications with HDF5 is that you go through the native virtual object layer of HDF5 that sits on MPI-IO, and then that MPI-IO layer talks to a parallel file system. That's the like white path on the diagram on the right. The HDF group, together with our team, has developed a DAOS, a virtual object layer, and through that you can cut out the MPI, you can cut out the parallel file system, and HDF5 data sets will be directly mapped to a container type that is not POSIX, right? That represents the HDF5 groups and data sets. And this is not only eliminating a part of the software stack, it's also giving us a hook to get around some of the limitations that HDF5 has. For example, because in normal HDF5 on files, you have to serialize when you create new objects. And the way the DAOS API is used, you actually don't have to do collective calls when you do like object creation, which can speed up the actual writing of your data sets significantly. There's direct access to the object class mechanism in DAOS through an HDF5 DAOS call, and we also introduced a key value type interface, especially for codes like particle in cell, where a particle is moving from cell to cell. This is way more flexible than arrays. The asynchronous API is also introduced here, so we can create event sets in HDF5 and then do all the operations asynchronously, and at the end just wait for that. So this is pretty powerful, and we're still also looking for examples from the community to run this and harden the code. Of course, this is all still pretty new, and we'd love to do more in the HDF5 area. All right, just a few pointers to other things. I mentioned the Python dictionary already. In the computational storage area, we have developed what we call a pipeline API. This is still pretty hard to use. There still needs to get some more like effort into this to make this more user-friendly, where the idea is to push some of the computations, like in a database, the where clause of an SQL query into the storage system, and then only get the results of those filters back to the application. And another prominent example is the parallel file in the the IO 500, where you can optimize the find operation, and we're doing something like that with the pipeline API as well. For the DAOS transactions, there is a persistent memory tutorial that Adrian Jackson from Edinburgh and our colleague Mohamed Sharabi usually hold at Supercomputing. I believe it will also be happening at the next Cray user group. And the example on the right here shows where you can open essentially a DAOS transaction, and you can do a lot of operations within that transaction. At the end, you commit. If there was no conflict, that commit will just go through and you're done. It's like an optimistic way to do parallel I/O, right? If there is a conflict with some other thread doing similar operations, then your transaction will fail and you have to restart it. That's an alternative to like being pessimistic and always locking and then getting performance degradations through locks. So those are pretty exciting, innovative things, but of course they need a bit more engagement than just mount a standard file system and be done with the POSIX interface. Okay, so just a few notes on what is out there in terms of actual systems right now. The biggest certainly is Aurora with 1,000 storage nodes, 16,000 NVMe disks, and 16,000 PMEM modules. LRZ in Germany is like a factor of 20 smaller. Both of those systems are on the compute side, Intel Ponte Vecchio systems. One is on Slingshot, the other one is InfiniBand. Ice Lake-based servers. And when you try to get a feeling of the performance of those systems, it's really hard. The IO 500, in my perspective, is not particularly useful, especially the scoring of the IO 500 is not very useful, although like the DAOS systems are on number 1 and number 2. The metrics that they're using are, I think, not really representative. Plus, you want to get something like a per server performance metric. So one exercise that we have been doing in order to get to as fair as possible a comparison was that we took 5 systems here that are all PCI Gen 4. They all have 2 200 gigabit network links. and PCI Gen 4 NVMe disks, and we divided the IO 500 numbers by just the number of servers to come up with the per server metric. And there's 12 tests in there, and I don't want to go through all of them, but certainly where DAOS shines is in the heavy metadata workloads and in the irregular IO space. So when you, what's highlighted here is like the IOR easy sequential stuff that every file system should be able to get good performance with those large sequential workloads. What you see here is there's still some difference, but I don't believe that Weka in yellow and GPFS in orange there is actually that bad. They should get better. That was probably just not a very good configuration from a customer perspective. What you also see is that the Aurora number 1 on the very left, the read is much slower than the write. That was an artifact of the slingshot Dragonfly topology, where the routes were actually not properly working. Okay. Where you see real differences is on the hard write and hard read front, where you write like 47 kilobytes unaligned, and the parallel file systems, in the write case, they go down to 0 point something gigabyte per second. Right? That's really the case where the versioning object store in DAOS gives you the maximum performance. And with enough tasks, you should actually be able to achieve the same as with the IOR easy workloads. So that's just a very short run through like where the performance is relative to some of the other solutions, but yeah, we can't go through too many other details here. If you want to learn more, there is the DAOS Foundation landing page at just daos.io. We have everything out in GitHub. Every feature branch for every customer where we do special things, it's all out in public, right? And it will be landed according to code reviews and gatekeeping that's happening on the foundation side. There's a mailing list, a Slack channel that's pretty active. So please go out there and look at what's happening, and if you want to get engaged, get in touch with me or somebody else in our team. So that's it for me. I'm happy to take any questions.